Anna Hoffman, and welcome to Data Exposed Live. Today is another special episode of our series, Something Old, Something New. Hey, Buck, how's it going?
It's going great, Anna. I mean, I miss being with everybody, but things are just going amazing.
Awesome. And for those of you who haven't tuned into Something Old, Something New before, this is a show hosted by myself and Buck Woody, who you see on the screen as well. And we tend to talk about data science topics. And, sometimes Buck gets on weird tangents. And, one of those tangents is I have to ask Buck, what does your shirt say today?
Oh, we've got another math shirt for you. I know you really enjoy the math shirts. So this one says,
I love math and cats.
There you go. With this shirt, you have to admit, you become instantly attractive to people. Very attractive. They really love math nerds and people who like cats.
I see. Yeah. I'm not sure if we should be saying that live on our channel, but you know what?
Again?
Yeah.
Yes,
we are live. Remember, these are always live.
Okay. All right. You have to remind me when we're live, Anna, the way it works.
Anyways, that being said, we are excited to have you guys here today. Just a reminder, if you do have questions, feel free to put them in the chat of wherever you are streaming from. We are streaming to Twitch, a few different Twitters, and YouTube. So please go ahead and put in your questions, say hi to us. Feel free to make comments about Buck's shirt or anything else you like. We're happy to try to answer, address, or just laugh with you.
Absolutely. And Anna, speaking of categorization, how do you tell the difference between an alligator and a crocodile?
I don't know, Buck. How do you tell the difference?
Well, you see one later and one after a while.
That one took me a second. I don't know where you come up with these things, but anyways, you said you wanted to talk about like order or something.
Yeah, absolutely. Today's episode, as we talked about, do kangaroos prefer cake or frosting, generally speaking? I mean, that's obvious, I think. People just always have a desire for order. People have always wanted to do this. Do you remember from school, did you ever learn Maslow's hierarchy of needs? Remember that one? Starts at the very bottom of a pyramid shape, like with safety, and then goes up through the self-actualization and all that sort of things. And once we can classify something, humans just do this: safe, not safe, food, not food. I tend to qualify everything as coffee or not coffee. Then we can deal with it, right? Once we've done that. And this idea of classifying things in a scientific way, kind of bringing more of the scientific rigor, really started kind of with biology. And it's called a taxonomy, which is from the Greek, taxinomia, or arrangement, that's taxi, and then nomia method, so arrangement method, right? And it identified animals into groups. And we remember the guy, Carl Linnaeus, hopefully I'm saying that correct. He started using a system, and we've adapted that to classify organisms to this day in this way. It's domain, kingdom, phylum, class, order, family, genus, species. And I learned this in school as, do kangaroos prefer cake or frosting, generally speaking, right? See, there it is. How did you learn
that? That's what the title was.
That's the title. Do kangaroos prefer cake or frosting, generally speaking? That's the way I learned it. Now,
I totally missed that. I did not learn that in school.
Oh, interesting. How did you learn it?
I don't even know that we had what are they called?
A mnemonic.
Mnemonic. Yeah, I don't think we had a mnemonic for this. The only mnemonic I remember was King Henry died Monday drinking chocolate milk. And that was how you did the metric conversions.
Metric. Yeah, metric is for the peasants, Anna. We don't do metrics in the US. I wanted to show you this. This is very cool. I found this thing from Quantum Magazine. It's a map of mathematics. This is just kind of a classification thing again, and what we do with it. Here's all the numbers and shapes and so on. I thought this was really neat, and I'll have a link to this for everybody. But you click on it, and it goes to an article on that particular topic. Isn't that just kind of cool to kind of see that the atoms are arithmetic, and it goes through and you get the map and all that kind of stuff. I just think that's kind of cool looking. So people just sort of do that. Now, taxonomy, and we call this taxonomy, in machine learning, it's more of a thing called classification. And we're basically classifying something into a group. You remember in our last couple of episodes, we've covered a lot the linear regression. Remember that? We tried to fit things close to a line. And then we talked about the fact that linear regression, which draws a line through some points, can be used not only to see how close something is to a line or predict the next number in that line, but it could also be used to separate the two data points into halves of that line. And that would be like a single classification. It's either this or it's that. And so we'll talk about that more in just a bit. But inside machine learning, the classification algorithms are used for lots of things, like sentiment analysis. So we think about whether someone likes us. You remember when you used to send those little notes? I like you. Do you like me? Check here, check me. You did send those, right?
Well, yeah, sure. Maybe we were using like AIM or something. I don't know that we ever were sending paper notes.
We had paper. Yeah, we had paper. And then, so that's a kind of sentiment analysis. Do you like me? Do I like you? It's actually a hard problem because you're going to take a corpus of text, a group of text, and you're going to try to say, is this positive or negative? And maybe it's both. You never know. And maybe you can show us a little bit about that later. We also think about spam, that email spam. That's just stuff we don't want and stuff you do want. And how do you tell the difference? Some of it's pretty obvious. You can look for certain words, but a lot of times this stuff gets really difficult to tell. The spammers are getting more intelligent, and so AI can wander across that and say, hey, when I see these things with these things, that's usually over here, and so that's a spam, not spam. That's a dual classification. Then there's document classification. And document classification can be things like, is this a legal contract, or is this something we have to take action on, and so on. And then, of course, the one we see a lot that you and I have already shown, in fact, is image classification.
Oh, so for sure.
Or a cat, right? And you said your dog is there with you today, right? And is he working, or is he just kind of hanging out?
Yeah, we should have some sort of classification model to classify what it is that he's actually doing. But right now he seems to thankfully be sleeping. But if that changes, I'm sure everyone will know.
No, that's a great classification technique. Awake or not awake, you have to mute. So there's a lot of other use cases. In fact, classification may be one of the largest use cases of machine learning that we work with at least today. Now, we've got our handy dandy cheat sheet there. Let me pop that back up because we've got a link to this, by the way, in our references section, but we've got this machine learning algorithm cheat sheet, and here it is. And you can see we've got different classification pieces. We did regression last time over here, these kind of things, the linear regression. Remember, we did that. And now what we're going to do is we're going to do this side, which is the image classifications, two-class classifications, and multi-class classifications. And we'll take a look at those sort of in more depth as we go along. But you know what? Let's dig in a little bit here. I want to dig into some of the classification algorithms. So in this part, I'll explain the primary algorithms we're using in machine learning for classification and taxonomies. And then I'll show you a little bit of the math for more information. Now, as always, you can spend a lot of time in the algorithms, and we'll give you references for those. And Anna will show you how to use libraries and packages just to simplify all that work. We think it's important to know the math and techniques behind each of your algorithms, but that doesn't mean you have to like memorize every statistical formula and so on. So here's a few of the classification algorithms we'll explore. I've arranged these in sort of math complexity and ease of understanding. This is just a wag from my side, but I think these are kind of these are kind of arranged in how easy it is to understand, and then how how you can work with them mathematically easily. Now, this is not a complete list. It does show some of the more popular ways that we use to classify things with machine learning. And as Anna and I go along, we'll build on that idea that you saw in the last episode. And remember, Anna, we talked about the loss and the error in regression. Remember those?
Oh, yeah.
Yeah. How could we forget, right? Nightmares. In classifications, you're going to do a lot of the same thing. But this is kind of interesting, Anna. In classifications, sometimes we try to maximize the likelihood of something in one group or another. And in other of these algorithms, you're going to minimize the error of not being in a group. So this is an interesting set of math here. You'll see where some are like, okay, do I belong to this group or do I not belong to that group? That kind of thing. Now, logistic regression, which we saw this one in the last episode, is a specific type of regression. Remember, we did linear regression, and then we talked about logistic regression. And this is a calculation that's used to get data to fit to align as closely as possible to predict a binary outcome. Either something happens or it doesn't, right? And I think I told you this before. I tend to classify people this way. For instance, for me, everyone is either Buck or not Buck. And see, you're in that second classification. You're a not Buck. And I have to always check and make sure which one that is. Now, naive Bayes calculates the possibility. This one's used a lot. So this is important to know. Naive Bayes calculates the possibility of whether a data point belongs within a certain category or it doesn't. It's based on something called Bayes, B-A-Y-S theorem. And I think that you remember that. We talked about that a little bit. And that basically says this: if event B has occurred, then we can find the probability of event A given B. Remember when you did the, do I want coffee or tea? Remember we did that?
Oh, yeah.
Carlo simulation and all those kind of things.
And if you knew that I had coffee,
right,
you could figure out what I wanted next.
Right.
Very important.
There's a great formula for that, and that's the one you use. But the problem is, even for small amounts of dimensions, the different factors involved, I mean, yours was just, did you have coffee before or tea before? It's one dimension. But if you had a lot of dimensions of things going on, like this happened, then that happened, then that happened, and this happened, and this, the data and the calculations for that gets really big and really quick. And naive Bayes, the reason it's got the word naive in it, basically just says, you know what? Every one of these features in the input vector, the stuff coming in, is just conditionally independent of the other features. What that means is I don't really care what happened. I'm just going to guess this one. That simplifies things a great deal, but you get the general idea. It works really well for large sets of data, and it's really useful in text analysis because you can use it to categorize words or phrases belonging to a preset sort of tag or classification, such as food or not food, buckwoody or not buckwoody. So that works out well. The next one is a clustering algorithm, and there's a bunch of these. These are sort of families of these things, just like we saw in our cheat sheet. And that's a pattern recognition algorithm, and it uses training data sets to find the closest number of relatives, usually denoted by the number K or groups, by iterating over that central point. It puts a center there and says, are you close? Are you close? Are you close? And of course, we have to have new names for things because that way you can make more money if you call things scientific names. And that's called a centroid. I had some centroids once, but I put cream on it and it's all cleared up. I'll show you the math
Okay.
One of those in a moment. Next is another cool one, support vector machines, or SVMs. And they train and classify data, and they use something called degrees of polarity, taking it to a degree beyond just a simple X or Y. So that's more useful. And I think you're going to show us one of those too. Decision trees are able to order classes on a precise level, and it works like a flow chart. It separates data points into similar categories, one or two categories at a time, from the tree trunk through the branches. It looks more like a root down to what we call the leaves, where the categories are more like, they're more similar, finitely similar. This creates categories within categories, which is really nice. And that allows us to do things with limited human supervision that we have to do. Now we're going to
Is this like, is a decision tree like what you showed us for picking the different model we should use? Is that a decision tree?
Very similar. Yeah. If we go back to, let me just pop that up real quick. If we go back to the cheat sheet, you can look at this almost to be a simple decision tree. What do you want to do? Do this. And you wanted to use 100 features, then here's what you want. So that would be a decision tree. Absolutely a style, but we just do it with math. Speaking of which, by the way, those are great, and they work very well. We're going to save neural networks, by the way, for an episode on their own. In general, they work using multiple layers or inputs, and that's where we get the term deep, of special purpose algorithms that act like a trigger of whether we send that value on to the next layer or not. And they're really helpful to work with images and things like that. They're hard to understand, but they're easy to work with because there's lots of libraries, as you know. So we'll cover that. We'll cover that later. So let's jump into the math, because I want to get to the section where you show us some of the cool stuff where we actually do it. So let's jump into the math. Awesome. Let's take a dig into the math with one of the most easy to understand classification methods. This one's called k-means. There's also something called k-nearest neighbors, and people tend to confuse those, but this is called k-means or k-space means. And it's kind of there in the name. It's a clustering algorithm, meaning it's going to put data together, and it's going to try to put data points together as close as it can based on how similar the features. Remember, features are just columns of data. Now remember, all statistics, we're just going to do this with statistics. There's our formula. It's basically folding things into a symbol and then unfolding that into more math, which probably has more symbols in it that you have to unfold again. You can kind of think about it like we're doing a PK zip, and that big sigma symbol right there means sum, as you can tell. SUM, sum. So we use a symbol, a picture's worth 1,000 words, to sort of PK zip a bunch of math into something like that. So it's formulas all the way down. As we work through some of the larger formulas, just kind of keep that in mind. For machine learning, most of the time we're dealing with formulas and techniques of combining formulas. So back in the last first episode, and I don't know if you can remember that far back, my memory is not what it used to be, but back in the first episode, we talked about supervised versus unsupervised methods. Do you remember that?
Oh yeah. So supervised is when you kind of have the answers or the labels available, and unsupervised is where you don't.
Right. So classification is interesting because it lives in both these areas. You can actually have some classification algorithms that are supervised that need an answer, and some are you just take a bunch of data and throw it on the ground and say, group that for me, because I don't know, right? And this makes sense when you think about it, because you're really trying to put something into a category and not predict the next number in a series. So you really don't need the answer ahead of time. K-means, the one we'll show here, is an unsupervised algorithm. We don't know the answers ahead of time in the source data. We just have a bunch of data and we say, figure it out. And the algorithm will take care of us. So what k-means does is it follows a series of steps that you repeat over and over until things don't change. At that point, you know you've hit bottom, and that's why I have this picture here. And you actually do this quite literally. It looks something like this. and we'll see how that works as we go. This shape is actually one of the representations of something called Euclidean distance, and we'll talk about what that means. So let's just break this down step by step for people. In the first step, we decide on the number of clusters, how many groups we want. This might be the grouping of customers, medicines, outbreaks, wins, whatever you want to classify. And you just sort of make this up. You say, I want 3 clusters or 10 or 4 or whatever. The more clusters you have, the less useful things become, if you think about it. When you start getting into like 30 clusters or 15 clusters,
Right.
what does that really mean? If you think about groups of customers, you want to sell to them, you want to market to them. So you'd like to know, how do our customers sort of group? So you just pick a number of how you do it. Now there are some various algorithms you can do to do this. But in general, you just pick the number. And by the way, that's the K in K-means. It means just a variable. I wish we could all just stick with X or Y, but apparently we need more letters in the alphabet. So then what we do after that, if we just pick a number, we said 3 or whatever we want. In step 2, what we're going to do is just grab some points and we're just going to assign them to a similar center. And you just do this by hand. Just group the numbers by number and say, I think those are together because they look alike or whatever. And there's various algorithms. There's one called the elbow method that can help you to do it.
Okay.
This is just your first wag. You're just giving it a general approximation as a starting point. Maybe the blanket that we have here with the 4 corners is just slowly drooping, but might be a little lopsided like this in math. So that's what we've done. Now, in step 3, we identify the centroids of the data. So once again, now that we picked our grouping, we need to figure out what's the center of that grouping. It's normally an average, right? And we just kind of pick and say, okay, well, that's probably the center. Now, maybe it's way off. You can see the pictures here. They just picked a number and said, this is the closest to where we think this is going to go. And then in step 4, we start doing some math. We try to weight the blanket, and we're going to do that using Euclidean distance. And let me show you a little quick article on Euclidean distance. And as we know, the most authoritative source of data is Wikipedia.
Of course.
But this one, the math ones, you can mostly trust. All right, here we go. You remember Euclidean space from school? I mean, obviously you remember Euclidean space. I mean, how could you not? But basically, Euclides picked a particular way of dealing with geometry in space, meaning not just 2 dimensions, but in multiple dimensions, an X, a Y, and then maybe a Z. And this is used in things all over the place, primarily physically in space. And then they said, how could we come up with a formula that would calculate the distance between 2 points in Euclidean space? So how far is something? Is there math we can do? And it turns out that there is. Now there's a very simple one you can do if there's only 1 dimension. If you've got 2 dimensions, it's got a slightly more involved function. And then it's got a much more genericized or higher plane of dimensions where we can do more dimensions. And we can go on and on and on and on, and we can use these very technical and things like that. So it's really useful. And by the way, we normally stop here and show you some of the hand math you can do for this. And that's just what I just showed you. But the good folks over at Learn by Marketing, you know my favorite tool. You know what my favorite tool is, right?
Excel.
Excel, that's right. The world runs on Excel. So the people that over at Learn by Marketing did a great customer segmentation. So basically they took some people that have bought things and they said, we're just going to group them into 3, and we're going to see what people in group cluster 1 bought. And we want to create a formula we can use that when we throw new data at it, it will just segment people into these 3 big groups, right? And so you can see this right here, the square root formula right here. This right here is just this. Well, this one, they're only doing 3, so they're doing this one right here. So you can see, you can actually, and Anna, I think you'll love this. I downloaded the spreadsheet And I took a look at it. Here's that formula. They've got that here. You got that look. Don't say it.
Well, can I say it?
Don't
I'm
say
going to say it.
You're going to say it.
Did you know that there's a add-in for this? I can actually, let me grab that. It'd be interesting to show them. Here you go.
All right, hold on just a second. You sent it to me. Let me look it up. Oh, really? Really? So just right inside Power BI. Look at there. And there it is. Look at that. It's got the whole thing, just a data mining add-in. So that's great. And thanks folks for tuning in. That was great. Next week, Anna will just show you another feature in Excel that I didn't know about. All right, here we go. All right, so we're on step 4 here. Thank you, Anna. We're on step 4 here. So here's what we do next. In step 5, now this is the magic, right? Now we can calculate the new centroids with those formulas to see how that works. Now, I want to show you. Actually, I don't have it up right now. I was going to show you. There's an actual graphic of this thing moving around, which is really cool, and you can play with it. I'll post it in the references links. But basically, you do this over and over, and if you were to watch it, the blanket will start moving around and then eventually settle into the bottom. We get to the bottom of things by continuously applying. And when the k-means algorithm doesn't change anymore, the answer is the same as the last answer, then it goes, okay, that's as close as they're going to get. And now you have your new centroids. Now that you have the centroid measurement, you can actually start feeding it new data that it hasn't seen, and it will group them together for you automatically. And you get those groupings, and the groupings are as accurate as they can be. Isn't that just cool?
Yeah, I think this is a really cool one. And for me, I start by looking at k nearest neighbors, which is similar, less intelligent, basically. The k you select here is just, okay, how many of the nearest neighbors are we going to use?
Right.
But k-means is much more interesting because you actually start to get into the math. And by just doing distance calculations like you would for a triangle or something,
right,
you can get pretty accurate clusters, pretty good clustering. So I like this one. Simple, but effective.
Well, why don't you take over now and give us some classification examples? Like, just tell us what's going on here as far as like some of the classification examples you know of, and you could show us maybe in a notebook or something.
Oh, yeah. So, yeah, let's definitely get into some new things. Someone actually commented something old is definitely Excel. So that was a pretty great comment. But, yeah, there are lots of things that you can do in, more I'm going to say different, not modern, but more different tools like R and Python. There are lots of different classification examples. For example, if you want to do medical predictions, this is something very common. There's actually a lot of different data sets out around things like predicting whether or not something is cancerous or not, or predicting how infertility might work for a second child. So there's lots of different things you can do in the medical space, obviously around classifications. We can also do things with SVM. So you talked about SVM, so we'll take a look at an example in Python.
Okay.
And then I have a few examples around decision trees, and then later we'll get to data mining. We're going to pull you in for that for sure. So with that being said, I'm going to head over to my notebook. You all know I love notebooks in Azure Data Studio. They're just really easy to use. And one of the best things is it allows you to combine of course, text cells or graphics cells that have this very interesting logo in them with runnable code, and the results get saved. So I love these. This is a SQL notebook. I'm connecting to a managed instance. So managed instance does support machine learning services in R and Python. And of course, from earlier episodes, you know that this has been in SQL Server as well for a while now. But so you could run this notebook in SQL Server or in Azure SQL Managed Instance. So that's kind of cool. Okay, so let's take a look at this first example. This one came straight out of the Microsoft documentation reference. We'll talk about where all these files are stored and how you can get access to them. But this one really with one line is basically creating a logistic regression model
Oh,
based on age, start, and number. And they're basically trying to classify whether or not something has the kyphosis, what would you call it, property. And what that is basically in your spine. It's how your spine moves. And some folks have a spine that kind of curves downward more or is rounder, and that's kyphosis.
okay.
So very easily you're able to predict whether or not this is happening or not in various patients given some sample data. So in this case, this is a supervised model. But one of the interesting things, just to call out how this works in SQL, is basically we're using this execute external script. We specify the language. So here we're using R. And then within the script, we can just say whatever it is we want to script. We can run our model. We can bring in other data. We can bring in data from within the databases that we have. And then we can store those models, or we can print some of the results. So see here, we're printing the results. And basically what it's saying, we're saying the number of independent variables, the number of observations, and then we get the coefficient. So we're going to get the intercept, because remember, this is a logistic regression. So we need the intercept, and then we need the coefficients for all our different variables.
Very cool. And that's the logistic regression part you talked about.
Exactly. So one line of code, we can do logistic regression. So that's pretty cool in R. And there's similar libraries in Python as well. Now, this other example that we have is around SVM. So, Buck, you talked about support vector machines, and these are really interesting, and you can do a lot of different things with them. For example, if you just have one class, and we were talking about this earlier, you can do anomaly detection with SVMs. And if you have two classes, you can do basically a very simple kind of linear SVM, which basically means, okay, we're going to find the two classes and just try to draw a line through them. And then if you have more than that, what you can do is we'll actually create, or these models can actually create hyperplanes. So they're kind of hard to think about visually how they might work, but they can actually figure out how to do the separation of different things. So in this example, we're just using kind of a pretty simple example. And, you know, libraries you know and love from Python, or if you don't know Python, libraries that you will learn to know and love, like NumPy and Matplotlib and sklearn.
Those are the big ones, aren't they? I mean, that's almost the 101 of machine learning in Python is those three, isn't it?
I mean, these three and pandas, and I think, yeah, you're golden. You can do a ton of stuff just with those. So pro tip, just learn those libraries. But basically what we're doing here is we're creating our own data set, and then we're going to try to split it ourselves. So we can simply use this SVM package to do a linear, to use a linear kernel to create the support vector machine.
Very cool. Very cool.
So once we plot it, you know, we can do some things to make the plot look nice. Now, again, what you'll notice is I am using this ML services. So here we're using the Python, and then I just have my script. Now, what's interesting here is when you're running in SQL Server, you can actually store this, save this as a PDF. And you can see, I went ahead and ran this just because it takes a few seconds. You can see what that looks like. So you can see what we're doing here is we're basically trying to find a way to separate, in this case, these two groups of points. So the way we do that is we're going to try to find the points that are the closest to the other cluster. So in this case, we're taking these points, and these are going to be our support vectors. So yeah, so what we mean by support vectors is we're going to try to maximize the distance between them and create a line. So that's where we get this line from. You can see it's right between these points, and it's also perpendicular to where these points are in relation to each other. So that's kind of how we come up with this line.
Yeah, so this actually illustrates what we were talking about earlier. Some of the algorithms, like the logistics, try to say how close to the line are you. This one is saying how far away are you. We're maximizing the distance from each other. The others, we were trying to minimize the difference in the k-means. We were trying to get as close as you can to the middle. This one is saying, no, just stay away from each other.
Yeah, exactly. So the opposite technique, but kind of achieves the same result. So it is interesting how we do different things here. I also, I also pulled this out into just a straight Python notebook. So you can
Uh-huh.
see, you're going to get almost the same result here
Hmm.
using Python versus using Python in SQL Server.
Right, right.
So it's
But
good to know that it's the same.
the neat thing you did there, though, you have R and Python in the same notebook.
Yeah, that's true. That's one of the beauties of using these SQL notebooks is I can basically specify what language I want the cell to be. So here it's Python and here it's R. So that's,
Nice.
yeah, pretty cool and pretty convenient for doing that. And when I'll show you where all these notebooks are so you can get hands-on and dive into the references here as well. Okay, so I have another example around decision trees. This is a built-in data set, but rather than focusing on the actual data set or the decision trees itself, I want to talk to folks. I'm not sure if we've talked about these packages, Microsoft ML or RevoScale Pi.
Yeah, we haven't mentioned that.
Yeah, so these are two really awesome packages that are shipped specifically for SQL Server, I believe. Is that right, Buck?
Yes. Well, RevoScale Pi is not just for SQL Server, it's for Microsoft's machine learning server. The Microsoft ML is for that as well. So you could get it in the standalone version. But interestingly enough, the standalone version of machine learning server is exactly the same as the one that's in machine learning services, because as we explained in the first episode, SQL Server just sends it across a secure memory channel to do the work and send it right back. So you have both. So yes, it's used in both.
Awesome. Yeah. So it's these packages, and what they contain is these libraries and other packages of models that people from Microsoft Research, as well as people from predecessors like Revolution Analytics, they've actually built these custom models. For example, we can use this RX Fast Trees, which is an implementation of Fast Rank. So this is a type of decision tree, but what it does is it creates the decision tree in a stepwise fashion. So it's really like a group of weaker prediction models, and then it decides what to use. And what's interesting about these types of models, decision trees, or at least I find it interesting, is you showed us kind of an example with your machine learning what to use when. That was kind of a form of a decision tree. But what you also have in classification models is you have this idea of a decision forest or a random forest. And so what you get in those models is, instead of making just one tree, we're going to use, maybe we'll use a certain number of folds, which we haven't talked about yet, but basically we'll make a bunch of trees. So that's why we call it a forest. And then we'll kind of put them all together to figure out what the best classification is going to be. So it's pretty cool how you go from decision trees to decision forests and random forests. And in Python, actually, I wanted to show this example. In Python, you can actually import, using, of course, favorite library, sklearn, you can import the decision tree classifier and the tree. And what this allows you to do is, after you create a classification model using decision trees, you can actually plot that tree. So for example, like you can see, I didn't have to write any code that figured out really how to plot a decision tree. This is for that iris data set, the famous flowers classification.
Really cool.
But it's really cool. You can see what the machine ended up coming up with from a splitting and a creating tree perspective. So all the way down to classifying what these flowers are.
Wow, that is so cool.
Yeah, pretty fun stuff. And the other thing I wanted to mention about these libraries before I got excited about decision trees and decision forests is that they are really great for working with in-database machine learning. But can you give people a refresher on what in-database machine learning is?
So whenever we talk about the machine learning, as Anna's been showing here, she can pop out and do Python on her own machine if she wanted to, or R, or anything else, any kind of libraries that she wants to run. And when she does that, she has to get data from somewhere. Now, in many cases, what we've been doing is just generating some data or using some built-in data sets. but we've shown you in past episodes, and you'll see in future ones, or you can perform a standard select statement in SQL Server to get the data. So for Anna to do her work, if she was the traditional data scientist sitting at her desktop, she would normally have to write an ODBC, an Open Database Connectivity Driver call that would call out to SQL, do the select statement over there, bring the data all the way back across the network, work with the data as much as she could stuff in memory, and which means we have to buy Anna a big expensive laptop instead of the Etch-a-Sketch we normally get her. And they then have to then work with that data and then send the results back potentially to reinsert the data in the database. Let's say we're making predictions of customers and we want to put them in groups. And so we now want a column that says, do the algorithm and put them in tell me what group they would be in, and it would put them in the groups. And then the marketing people could bring up a Power BI report that says, these are our stay-at-home uncles that buy diapers on Thursdays. Maybe that's the grouping or whatever. And we want to send them a special coupon, right? And that's what we want to do. So that's what the traditional is. Well, we got a bunch of problems here. We're sucking tons of data across the network. We're dependent on Anna's machine being large enough to do the work. We're pushing all the data back. All those are locks. All of those are consistency issues, not to mention security. She's pulled all that data down onto her laptop. What if she could do the work on SQL Server, have it get the data from SQL Server and do the machine learning in SQL Server and store the results in SQL Server? And the data never went anywhere. But she could still do all the work. And in fact, she could do it on a browser if she needed to. What if we could do that? And that's the beauty of in database. So it's performance, it's security, and it's optimization of resources.
Yeah, definitely. And like Buck was mentioning, I can actually access that data using some of these packages that come in, for example, in the RevoScale ETL library. And there's also just RevoScale for R as well. But with this RX data step, we can do things like bring in that data. So when we use RX Predict, for example, we can specify what the data is. Now, in this case, we're just using some data from our train test split from a built-in data set, but it's possible that this data set is actually a query that's been run in the database, and we can do all of this in the database. So it's very powerful.
And you could even create your model out on your box with a smaller toy set of data. Toy set of data means fake data that looks a lot like the real data. Get it all modeled the way you want to. Once you create your model, you could give it to the database administrator, who simply puts this code in SQL for you, and you never get to see that data. Maybe you're going to do some work on HR and salaries, but they don't want you to be able to see that. But you can fake up some data, get the model correct, give it to the DBA. The DBA runs the stored procedure, and now people just call the stored procedure, the model runs, and you get a result. Nobody gets to look at the HR data.
Yeah, exactly. One of our viewers said analytics where the data lives, which is exactly what we're going for. So
that's exactly right.
Great comment. And like Buck mentioned, using things like the machine learning extension in Azure Data Studio, you can actually import models from other places, right? So like Buck was mentioning, maybe I train my model locally and now I want to deploy it to my managed instance or my SQL Server. I can actually do that from here. All right, so we have one more, well, it's kind of a double example, but we have one more example, and this is about naive Bayes. So like Buck was mentioning, we talked about this way of using probabilities to kind of make predictions. So in this scenario, so if we think about this scenario, what we're doing is we're trying to understand who would buy bikes. And so we work for Adventure Work Cycles, which is a company maybe you've heard of. It's a fake company, but they're very popular among the SQL Server community for buying and selling bikes and looking at their databases. But basically, we're trying to understand if a customer is likely to buy a bike, because if they are, then maybe we want to send them some promotional mail or that sort of thing. Now, something you can get in SSDT, which maybe some of you are familiar with, it's SQL Server Data Tools. This is a really useful, in my opinion, underrated tool, but this tool can actually do a lot of things for you with what it's called, I think it's called the naive Bayes viewer, model viewer. So for example, what I can do if I hop over here, I can take a look at this example. Let me just make that a little bigger. So what SSDT allows us to do is basically take in the different attributes for a given potential customer and figure out their likelihood of buying a bike. So we have some labeled data, and so we see the total population. So this is allowing us to look at the distribution of each topic. For example, if we say age, we can see those first 3, yellow, red, blue, represent different age ranges, and then the gray is an other. Same for commute distance, education. So this is allowing us to look at the different distributions overall. And then if you look at 0, these are people who historically have not purchased a bike. So for example, something that you might find interesting is if we look at, and then the 1 is those who have purchased a bike. But if we look, for example, at commute distance. Now, if your commute distance is 2 to 5 miles, maybe that's a little long to commute via bike, right? But if you live less than a mile from work, maybe commuting by bike, is more likely. And what we can see in the data is that distribution, so this yellow bar, is bigger in people that buy bikes. So that means, living closer to where you work may make you more likely, the probability is higher that you would buy a bike. And similarly, let's see, if you have, this is another interesting one, number of cars owned. So it says, okay, if you own 2 cars, so that's the yellow. If you own 2 cars, you can see the yellow box is much bigger compared to the yellow box if you bought a bike. But if you own 2 cars, then you're probably not buying a bike because, both the heads of your household potentially have cars. So you have no reason to buy a bike. So this is a really interesting way that SQL Server and SQL Server Data Tools kind of just visualizes that for you. And then on top of that, we even have, and we'll share again a link to this, we even have ways for you to query this data. Now this enters kind of an interesting, let me just show you, so you can actually query some of those things from the mining model. So can we take a step back, Buck? Can you tell us what is this idea of data mining? And it sounds kind of like machine learning.
Yeah. So let me get the time stone out, right? And I'll get the time stone and I'll turn our time stone back to the 90s. I'm not even going to ask you if you were around in the 90s, but at any rate, back in the 90s, we went from starting even before that. Let me take the time stone and turn it back some more. In the 70s, we had artificial intelligence came out, right? Everybody was the talk of the town. A lot of it was like fuzzy logic and some of the other things that we talked about in the very first episode. And these days, and I'm not sure how I feel about this, but the technical term for that is good old-fashioned AI. So some of those techniques and some of the math was not nearly as sophisticated as it is now and didn't work over large pieces of data. But in the 1980s, we began to collect more and more data, and this term came around called a data warehouse. And the data warehouse just meant a trough of data where you didn't start getting rid of things. Back in the day, it was very expensive to store data, so you get rid of it. If you didn't need it, you just got rid of it. And nowadays, you just keep everything. So as we began to have these huge amounts of data, you got past where you could do an easy query. It was just kind of harder to do. So we wanted to start using that data and start performing some actions on it. So we had this thing called data mining. And data mining, it's loosely defined as the process of uncovering patterns in data and other valuable information from data sets. Fine, that's
okay.
Broad, and it sounds just like what we call data science now. But it also, by the way, used to be called KDD, or knowledge discovery in data. In general, this was just a move to do more with the data we were storing in those data warehouses, large data stores. Most of the time, the data mining system was a single box. It was just one system. In fact, you may not know this, but in SQL Server, you can have data mining. There's a data mining feature, and it's what Anna just showed you. It's built right in, and many times it's all you need. Now, if artificial intelligence and data mining got together and had a baby, that would be called machine learning. That's what we do with machine learning today. So you'll see a lot of the early precursors and vestiges of data mining in machine learning. But again, normally it was limited to a single box, even though it could do a lot of really good stuff. It could do things like anomaly detection. That was very common. Outliers, changes in data, deviation detection, things like that. It could do association rule learning, which was called dependency modeling. And basically, this is just relationships between variables. Basically, a supermarket runs a sale, you buy a steak, and then that's what they know. Clustering, as we've just talked about, it did that very well and does that very well. Classification, it does classifications really well. It does regressions really well. And it does something we used to call summarization, which is basically just sort of compacting the data into something you could look at quickly. Now, many of the algorithms we're using in machine learning today are similar or exactly the same that you would see in data mining. But with our newer technologies, servers and storage and so on, we can reference more data, and we can do that on distributed storage and distributed processing. So this is a little different than what we would do in data mining. We also have access to new families of algorithms, deep learning, and so on. It doesn't mean data mining is gone and doesn't still have a place. In fact, the team data science process, aka.ms/TDSP, team data science process, I helped build that. That's built on the CRISP DM, the cross something industry process for data mining, right? That's literally what CRISP-DM stood for. And if you look at it, it is very similar to the team data science process. Difference in TDSP is that it's for more of a bigger team distributed across multiple features. So that's kind of where you have. And Anna, you've now showed us that we have the data mining stuff still around and still quite useful.
Yeah, definitely. And it seems like there's a lot of overlap there in capabilities and, just reasons you would use it. So very relevant today. I have one more example.
Okay.
This one is in R. It is related to using naive Bayes again. Now, one thing that happened, and I thought this was interesting to share with you all, is I was using R and I was trying to install some packages that I use. Maybe some of you are familiar with Caret. It's a very popular package in R. But I got an error saying that, we didn't have these libraries available. Now, there are some ways that you can install libraries, and I wanted to show you with the machine learning extension in Azure Data Studio. If you hit manage packages in the database, you're actually able to go and view and change the packages that are available in both Python and R. Now, in R, it's not on by default, but there is a way to turn that on. So just a little tip there. Now, since I don't have time to do that today, what I did is I actually did this in R Studio. So this is the tool, kind of my go-to tool for doing R workloads. And so you can see I'm able to do all this. And the thing I wanted to call out is it's that same iris data set, but you get a confusion matrix. Now, this is something
about that, didn't we?
talked about. Exactly. So this is something that, a skill that you learned that also, very much relates here in understanding, how your predictions did. So for example, you can see in this model, this naive Bayes model, we were able to 100% correctly classify all the Setosa flowers. However, the prediction for the versicolor, what we can see is 17 of them did match up with what they were actually labeled, but one we misclassified. So this is a very useful thing, and we get some other statistics here you might want to check into. The other thing I wanted to mention is when Buck was talking about accessing data outside of SQL Server, this is how you have to do it sometimes. You have to connect with an ODBC type of driver. You have to bring in a library, and you have to bring all the data in. And like Buck said, down to my local, which is sometimes there's a reason for that, but sometimes, it's less than ideal. So, Buck, we've really talked about a lot today. I hope it's been useful for people. I've actually learned quite a bit from your your math, and it's been a good refresher for me to remember things like k-means and why we use classification.
Right. No, it's a good stuff. And Anna, I think we have all these resources available for them out on aka.ms / and it's something old, something new, SOSN. That's all you got to type, aka.ms / SOSN. There, Anna has it up there, and you can see we've just got everything there. And as Anna scrolls down, you'll see all the episodes are here. And we'll update this one with the latest video. But there's all of the links that we showed with the Excel file and the embarrassing thing where we already have it for you, and the rest. And we go all the way back to episode 1. And then if you click on, we have the notebooks in there. All of Anna's notebooks are available. And then if you click on any of the videos, it goes straight to the video. And we also have this, it's just a prettied up GitHub view. So as you click on it, you'll see that you're just in the GitHub. And there's all of our notebooks. Why don't you click on one of those notebooks, Anna, just so people can see. There's one from there. And the neat thing about GitHub is that most of the time it renders. It won't when we're like, oh, it did.
It did. Yeah.
It will actually run the notebook or show the results of the notebook that was run. So you can actually follow along with us, and you can try these on your own machine. So that's awesome.
Yeah, definitely very cool. As we go towards closing out this episode, I wanted to give a shameless plug for something we're doing in a little bit. I hope that was okay, Buck. But we have next week, it's on Tuesday, this really big Azure SQL digital event. Rohan Kumar, our CVP of all of Azure Data, is coming to talk to you about the latest innovations in Azure SQL, as well as how we are innovating going forward. And there's really awesome segments from folks like Bob Ward, folks like myself. We did a pretty cool demo, actually 2 cool demos, so you want to check that out. And then we even have demos from people from the community, so this is a great way to get involved and see what's going on. Now, after that, commercial from me, I did want to say, Buck, can you give us kind of a sneak peek at what is next for this series we're doing?
No.
No?
I haven't made it yet. I told you, you have to tell me when we're live.
Yes, well, we are still live, but Claudio said that as a DBA, seeing all the machine learning stuff is very tempting, very interesting, and cool. R in SSMS. Yes, you can do R in SSMS.
Yeah. Yeah, and Claudio, don't be afraid to dip in. Start with episode 1. Follow the links. I think you'll really, really, really like what you've learned there. We have fun with the math. We have a really great time with this, but you don't have to learn the math. That's the beauty of this. There's so much already done for you. Anna and I both have done sessions that you can find on Channel 9 and elsewhere about making calls out to pre-built AI from inside SQL Server. So you don't have to do any machine learning if you don't want to, but you can still get the benefits of it. So that's awesome. Well, Anna, I think we need to turn this over to our executive producer, our senior executive producer, and let her take us out. Marisa, are you still around?
I'm here, and thank you for the upgraded title there, executive.
No problem. Those are free, so you can be if you'd like to be the emperor senior executive producer.
There's an idea for sure.
Well, thanks so much, folks. I'll pass it over to Marisa, but we do hope to see you next time on Data Exposed.
Absolutely. We'll come up with something to say, we promise.
We appreciate y'all joining us every week for Data Exposed Live. This week, we'd like to give a special thanks to Wolfgang Pauli, Jeremy Reynolds, the 1690s and 1735, respectively, Learn TV, Channel 9, and as always, produced by myself, Marisa Brazili, and Anna Hoffman. See you next time on Data Exposed Live.